Find the limit. In the first example, the limit as x approaches 7 of 5x over square root of x plus 2. You can simply substitute 7 in for any x that you see in the expression. And that's because when you substitute this 7 in for the x into the denominator, this does not create a division by 0. So this limit will equal 5 times 7 over the square root of 7 plus 2. And so in the numerator, you'll end up with 35, and in the denominator, you'll end up with the square root of 9, which is 35 over 3. In this next example, we can try to do the same thing. We can take this 0 and try to substitute it in for all the thetas that are here. And when you do that, you'll see that you end up with a 0 divided by 0. This is what we call an indeterminate form, and this means that we are not able to just directly substitute this 0 in for the theta. However, this indeterminate form lets us know that we can do something about how this is written. Maybe we can rewrite it some way and some terms can cancel out here. So the limit as theta approaches 0, I know I can rewrite the tangent squared as sine squared theta over cosine squared theta. So that's the numerator, that was this part here. So I know I can rewrite that part. And this is all still divided by theta sine theta. Now in this blue box, I have a fraction within a larger fraction. And it would be great if I didn't have this fraction within a fraction. So what I'm going to do off to the side here is I'm going to multiply this big fraction by the denominator of the small fraction. So if I multiply this in the blue box by cosine squared x, that cosine squared x in the denominator won't be there anymore. Cosine squared x, cosine squared x. So that allows me to cancel this and write a new limit like this. From here, now it is rather clear to see that I can cancel a sign in the denominator with a sign in the numerator. So I will still have a sign left in the top here, and the limit can be rewritten as such. So what I've done is I've separated out this portion of the limit, this sign that was left over in the numerator and the theta in the denominator. And if you separate that out, that leaves you with a 1 in the numerator. And on the right side down here, I have that 1 over cosine squared. So I know that the special trig limit, the limit as theta approaches 0 of sine theta over theta, I know that's 1. So this whole thing ends up being 1 times 1 over cosine squared theta. Now I can directly substitute this 0 right in here for that theta, because the cosine of 0 is 1. So now I have this. So our answer here is 1, and that's because the sine theta over theta is 1. That's this red one here. And then I substituted the 0 in for cosine, and cosine of 0, that should be 0, not theta. The cosine of 0 is 1. So if you square 1, you get 1. 1 divided by 1 is 1. 1 times 1 is, the whole thing is 1. Find the limit. On this page we have two examples. And the first example is the limit as x approaches pi over 2 of cosine over cotangent. And if you try directly substituting this pi over 2 right in for the x's in the limit, you'll end up getting a 0 over 0. And this is an indication that something isn't quite right about this limit, and we can do something about it. So the first thing I want to do is rewrite this limit as x approaches pi over 2 of cosine x all over cotangent can be rewritten as cosine x over sine x. Now, as in a previous example, I want to multiply this big fraction right here by the denominator of the fraction down here, by the sine x. Sine x. What that allows me to do is cancel out the sine x's in the denominator, and I can now rewrite the limit like this. So here, now that the limit is rewritten, you can see pretty clearly that a cosine can be canceled, and now I can write the limit as x approaches pi over 2 of sine of x, and I can directly substitute this in now and get an answer of 1, because the sine of pi over 2 is 1. Now similarly with this second example, if I try to substitute 2 in for x here and here, I end up with a 4 plus 1 over 0. Now this is a little different than this. Here we had a 0 over 0. This meant I could manipulate something in this expression so that we can cancel it out. Over here I have 1 over 0. This is not in indeterminate form, this is just undefined. When you have a number that's not 0 divided by 0, this means we will definitely end up having a vertical asymptote. And in fact, this vertical asymptote is at x equals 2. So what will need to happen is we will need to make a table of values like this. And I pick these values, 1.9, 1.99, 1.999, and so on, because way back here at the beginning, this said 2 from the left. This is a one-sided limit. So we have x approaching 2 from the left. That means we need numbers less than 2 that keep getting closer and closer and closer to 2. So, and really quickly I want to mention here, there is no function up here. This is the limit of some algebraic expression. So I'm going to simply call f of x this entire expression in the parentheses. So what I'll be doing is I will be substituting 1.9 in for x, 1.99 in for x, and so on. And when you do that, you end up with this list of values. And as I tried to write these values in, I realized that I was going to run out of space here. So this last number is negative 9,996.0003. So let's look at this table as a whole. So these numbers, these x values, they are approaching 2, just like we want our limit to do. They're approaching 2 from the left side of 2. And when you look at these f of x values, these are getting bigger and bigger and bigger in the negative direction. So this means these are going to negative infinity. And this is the way you work with finding a limit as you approach a vertical asymptote. So we can write that the limit as x approaches 2 from the left of x squared plus 1 over x minus 2 equals negative infinity. Find the limit. The limit as x approaches 0 of cosecant pi x. One way to work through this limit is to remember that the cosecant is the reciprocal of the sine function. like this. From here, you can try direct substitution by trying to substitute the 0 in for x. And when you do that, in the denominator, you'll have sine of pi times 0, which is sine of 0, which is 0. So when you try to directly substitute this in here, you'll end up with 1 divided by 0. And what happens with that is you will not be able to manipulate this in any way, shape, or form in order to cancel out the problem. So knowing this, there is going to be a vertical asymptote at x equals 0. And if you look at the graph of a cosecant function, there's definitely a vertical asymptote at x equals 0. So that means we need to create a table of values, something that looks like this. I have a table broken apart into 2 rows, and that is because since there is no indicator telling whether or not this limit is coming from the left or from the right, we need to check both sides just to see if these will be going to the same sign infinity. So I want to make a point really quick. In these tables I have x and f of x and x and f of x, and there's no function listed up here, but I will be calling the cosecant of pi x f of x. So now we can start filling in this table. And when you substitute all of these x values in the top table, you can see that these values are approaching 0 from the left side. And as that happens, the y values, or the function values, approach negative infinity. But in the second table, as we approach 0 from the right side, you can see that the y values are going to positive infinity. And for this limit to equal an infinity, the signs have to match. You can see here's a negative infinity, here's a positive infinity. Those signs do not match. So this limit does not exist. In this second example over here on the right, you can see we have the limit as x approaches 3 of the square root of x plus 1 minus 2 over x minus 3. And again, if you substitute this 3 in for each x, you'll end up with a 0 over 0. That means we need to somehow cancel something out in order to make this limit workable. So in order to do that, we need to rationalize the numerator. So what that's going to look like is you'll have the limit as x approaches 3 of the square root of x plus 1 minus 2 all over x minus 3. And we're going to multiply this fraction by the conjugate pair of the numerator. That is the square root of x plus 1 plus 2 all over the square root of x plus 1 plus 2. So when we do this, you'll multiply the numerator of that fraction times the numerator of that fraction, and the denominator of that fraction times the denominator of that fraction. And one thing that I want to point out here is that when you multiply the denominators together, don't FOIL this thing out. Do not expand this. Don't distribute these. Leave these as is, and you'll see why in the next step, or in couple steps. So the numerator, yes, you want to FOIL all of this out, and you'll get a limit that looks like this. So when you multiply these two binomials together, you'll get this expression in the numerator here. And the next step is to simplify that numerator. So you'll have the limit as x approaches 3 of x minus 3 all over x minus 3 times the square root of x plus 1 plus 2. Lo and behold, we can reduce the x minus 3's. So that'll leave you with a 1 in the numerator, and you'll have a limit that looks like this. And at this point, we can now directly substitute this 3 in for that x, and when you simplify all of that down, you'll end up with the limit equaling 1/4. Find the limit. For this first example here on the left, we have the limit of delta as delta x approaches 0 of x plus delta x squared minus x squared all over delta x. And again, if you try to substitute this 0 in for delta x, you end up getting a 0 over 0. Again, indeterminate form, that means we might be able to manipulate this expression so that we can cancel something out somewhere to be able to substitute 0 in for delta x. Let's see if we can do that. So this will be equal to the limit as delta x approaches 0. It doesn't look like I can do much here except for maybe expand this binomial. So let's call that x squared plus 2x delta x plus delta x squared minus x squared all over delta x. And it looks like that since we expanded that binomial, we can now cancel an x squared with a minus x squared in the numerator. And now I'm going to rewrite the limit to clean it up. Here it is without those x squareds. Let's see, can we substitute 0 in now? If we did that, we'd end up with a 0 in the denominator. That's pretty easy to see. And if we substitute a 0 here for delta x, that means we would still get a 0 plus another 0. This still gives us a 0 divided by 0. We have to do something here. Oh, I see. So if you notice in the first term, there's a delta x, and in the second term, there's a delta x squared. That means we can factor one out. That'll look like this. So now that that delta x has been factored out, we can cancel a delta x in the numerator and the denominator. From here, I want to rewrite this limit. This is the limit as delta x approaches 0 of 2x plus delta x. So now we can just directly substitute this in here and get a final answer of 2x. If you substitute 0 in for delta x, that's 2x plus 0. Well, if you add 0 to anything, you just get itself back. 2x is your answer here. For this next example, I want to check what happens if I directly substitute 1 in for all these x's here. In the numerator, I'll have 1 squared is 1, 1 minus 1, that'll give me a 0. And in the denominator, I'll have this set of parentheses will equal 2 times 0. So that is also over 0. So I hope you're seeing the pattern. If you try to directly substitute something in and you get a 0 over 0, some simplification can happen here. So let's see what that looks like. We can rewrite this limit as x approaches 1 of x times x minus 1 all over x squared plus 1 times x minus 1. So if you see that you can common factor out this x in the numerator to get you this expression, now these x minus 1's in the numerator and denominator will cancel out, and it'll leave you with this limit. Now we can directly substitute this 1 in for x here and here, and that will give you 1 over 1 squared plus 1, which is the same thing as writing 1 over 2. So as you're going through and figuring out this example, make sure you simplify this down to 1/2. You don't want to leave this like this. Simplify it down to 1/2. Find the limit. Again, 2 examples. In this first example, we have the limit as x approaches -3 from the left of x squared minus 9 over x squared minus x minus 12. My first step is to directly substitute a -3. Don't worry about it approaching from the left. But I want to substitute this -3 in for every x that I see. So here, x squared minus 9, that gives me a 0 when I substitute -3 in for x. And in the denominator, if I put -3 here, that'll give me 9. Minus a -3 is positive 3. So 9 plus 3 is 12. Minus 12 is 0. Well, look at that. We have an indeterminate form, 0 over 0. That means I should be able to manipulate this expression somehow to cancel something out. Here we go. This is the limit as x approaches -3 from the left of x plus 3 times x minus 3 all over x plus 3 times x minus 4. So I factored the numerator by difference of squares, factored the denominator to get this new expression. And now I can reduce away the x plus 3's. The limit as x approaches -3 from the left of x minus 3 over x minus 4. So now if I substitute this -3 in, and yes, you're allowed to substitute this -3 in even though it says coming from the left. If there are no vertical asymptotes and no restrictions on you substituting this -3 in, then you can just substitute it in, whether it's coming from the left, from the right, or from both sides. So I can substitute in this -3 to get this limit equaling -3. I'm going to put it in the numerator and denominator right away. -3 minus 3 in the numerator, -3 minus 4 in the denominator, to get -6 over -7, which is 6 over 7. So there's your answer for the first limit here. And I realize now that this second example, this limit, is out of order from how I want to go over these limits. So I will do this example in a couple pages. Find the limit. In this first example, we have the limit as x approaches infinity of 3 minus 2x all over 3x cubed minus 1. And this really gets to the heart of a previous idea that you've learned maybe in college algebra, algebra 2, or pre-calculus, what the horizontal asymptote of a rational function is. So you would know that since the degree of the denominator is greater than the degree of the numerator, that this horizontal asymptote is y equals 0. The calculus behind it is we are really interested where x is going as a new end behavior when you learn about it in a previous course. So how do we figure this out? Well, we have to remember this limit. I'm going to write it all the way over on the right hand side here. The limit as x approaches infinity of a constant over x to the n power, where n is some positive power, equals 0. So we're going to use this idea a lot on this page. So in order to figure out where this limit is going, I mean, we already have an idea that it should be going to 0 because of previous knowledge, but how to show it, how to prove it, we need to take the limit as x approaches infinity of 3 minus 2x all over 3x cubed minus 1. And you may notice that I wrote this a little weird, but we want to divide each term in the denominator and each term in the numerator by the highest power of x in the denominator. So the x cubed is the biggest power of x in the denominator, so I'm dividing everything by x cubed. And when you simplify all this, you'll get a limit that looks like this. So all I did was go through and cancel x's where I could. I could not cancel any x's here. 3 over x cubed is 3 over x cubed. 2x over x cubed, I can cancel 1x. That became 2 over x squared. 3x cubed over x cubed became 3. Those both cancel out. And 1 over x cubed is 1 over x cubed. So now we get to use this theorem over here on the right. This says the limit as x approaches infinity of something over x to some positive power equals 0. So this, in blue, I'm going to highlight these here. So this fits this scenario over here as well as these other two. So the limit as x goes to infinity of this is 0, 0, 0. So those all go to 0. This leaves me with 0 minus 0 over 3 minus 0, which is 0. Cool, that matched up exactly with what we thought was going to happen, but now we have a way to prove it. All right, so in the second example, something very similar is going to happen. You can use the rules that you learned from a previous course to probably understand what the answer is here. But in order to use the calculus, we will write the limit as x approaches infinity of 3 minus 2x all over 3x minus 1. And again, I'm going to divide all of these by x. I'm going to divide all of these by x, just by the highest power of x in the denominator. And here in the denominator, the highest power of x is x to the first power. So when you simplify this limit down, you'll get something that looks like this. And in this example, there are only two parts that will go to 0. So what are we left with is 0 minus 2 over 3 minus 0, which is the same thing as writing negative 2 thirds. And this matches up exactly with what you would think from previous course. The degrees of the numerator and denominator match. So you just take the ratio of the leading coefficients, the negative 2 over the 3. Look at that. So now again, we are able to prove what happens as x goes way out with a horizontal asymptote. In this last example, we're going to do the same thing as we did in this example. Divide all the terms by the highest power of x in the denominator, that is x to the first power. It'll look something like this. So I've already divided all of the terms by x over here and simplified everything. And I know that this portion and this portion are going to go to 0. And so that leaves me with the limit as x approaches infinity of negative 2x over 3. Well, as x goes to infinity, those are really, really large numbers. And if you are multiplying very, very, very large numbers by negative 2 thirds, that means you're going to have really large negative numbers. So this limit actually goes to negative infinity. And that makes sense as well in college algebra, pre-calculus algebra 2, whatever. We said if the degree in the numerator is bigger than the degree in the denominator, there is no horizontal asymptote. In fact, it has an oblique asymptote. And if you divide these polynomials out, you can find what the oblique asymptote is, and as the function moves further and further and further to the right, it will also go further and further and further down. Find the limit. In this example, it's very similar to the previous 3 examples you just saw. I am going to let you all go through and divide everything by x to the 3/2 power, because that is the biggest power of x in the denominator. And I want you to actually go through and do this one, and you should get an answer of 5/3 when you're all done. The example I'm interested in is over here. This is the one that I skipped earlier in the video. This is the limit as x approaches infinity of 3x plus 1 over the square root of x squared plus x. This is done similarly to the previous 4 examples, as we need to divide by the highest power of x in the denominator, because that's what you do when x approaches infinity. However, we're going to represent this a different way, and that is we need to know that the square root of x squared equals the absolute value of x. So in the denominator, we will be dividing everything inside the square root by the square root of x squared, and everything in the numerator by the absolute value of x, because that's what is equal to the square root of x squared. So this limit will be the limit as x approaches infinity of 3x plus 1 all over the square root of x squared minus x, plus x. And in the numerator, I'm going to be dividing by the absolute value of x, and in the denominator, I'm going to be dividing by x squared, both of these. Now, these are on the inside of the square root. So when I say I'm dividing both terms inside the square root by x squared, I'm really dividing by the square root of x squared, both terms. So this is still an equal fraction to what we started with up here. And I just realized that this infinity needs to be negative. There we go. So when we look at this, I can simplify the bottom pretty well. That just ends up being the limit as x approaches negative infinity of the square root of 1 plus 1 over x. So all of this is inside the square root. In the numerator now, I can't just divide x by the absolute value of x, or 1 by the absolute value of x. What else needs to happen is you need to take into account which sign infinity you're going to. So this, negative infinity, tells us that the absolute value of x is equal to negative x. And once we make this switch right here, we can then start simplifying what's in the numerator. So I'm going to rewrite this as 3x plus 1 over negative x over negative x. So now I can start simplifying this stuff down. So the x in the top and the x in the bottom here will cancel, and this will leave me with a limit as x approaches negative infinity of negative 3 minus 1 over x. This minus sign comes from the fact that you're adding a negative fraction, so it's minus that, all over the square root of 1 plus 1 over x. So again, I can state that this thing goes to 0, this part goes to 0, so you're just left with a negative 3 over square root of 1, which is negative 3. And if you go through and try doing the same limit that we started with, but go to positive infinity like I had originally written, this entire limit will go to positive 3. I encourage you to try that, reason through why you can get from positive infinity here all the way down to an answer of 3 down here.